Right. Hello all. In my previous class, I discussed effect of doping on energy band diagram and p-type semiconductor and its electrical characteristics. That is charge neutrality of p-type semiconductor. Next, calculation of conductivity of a p-type semiconductor. And also I discussed Fermi level of a p-type semiconductor. Calculation of Fermi level of p-type semiconductor. Right. Now, in this class, actually, I will start with questions. Right. In your classroom workbook, the question number 4. Right, in question number 4. A pure silicon sample is doped with. A pure silicon sample is doped with 10 power 14 boron atoms. 10 power 14 boron atoms. If Ni equal to 1.5 into 10 power 10, if Ni equal to 1.5 into 10 power 10 per centimeter cube, comma, mu p equal to 500 centimeter square per v second, 500 centimeter square per v second. Find first bit carrier concentration, and conductivity. Second bit Fermi level with respect to EV. If NV equal to 26.6 into 10 power 18 per centimeter cube. Right. Yeah. All of you read the question once actually. See, they given a pure silicon sample, right? It is doped with boron. How much amount? 10 power 14. Nothing but this is acceptor concentration, right? Also they given Ni equal to how much? 1.5 into 10 power 10, right? Also they given 500, mu p equal to how much? 500 centimeter square per volt second. Yeah. What we want to calculate actually? Carrier concentration. See, for calculation of the carrier concentration, we have two formulas, exact formula and approximate formula. See, for this example, which formula is applicable? See here, Na is 10 power 14, Ni is 1.5 into 10 power 10. So clearly here, the acceptor concentration is far greater than Ni. If acceptor concentration is far greater than Ni, then what about the whole concentration? Actually, the whole concentration is nothing but acceptor concentration. Approximation, right? So, which is equal to 10 power 14 per centimeter cube. And how to calculate electron concentration? Actually, Np equal to Ni square by Na. What is Na here? 1.5 into 10 power 10 whole square by Na. Na is nothing but 10 power 14. So, which is equal to 2.25 into 10 to the power of 6 per centimeter cube. This is the first carrier concentration. And one more we want to calculate, that is conductivity, right? That is sigma p. So, what is the conductivity actually? Sigma p equal to Na into E into mu p. What is Na here actually? Na is nothing but 10 power 14 charge of electron 1.6 into 10 power minus 19 coulombs. And mu p equal to 500. So, which is equal to 0.008 ohm centimeter whole power inverse. This is the carrier concentration and conductivity, right? And the second bit actually, what is the second bit? Fermi level with respect to EV. See, it is a p-type semiconductor. That means we have to calculate EFP with respect to what actually? With respect to EV. That means EFP minus EV we want to calculate. What is the equation actually? EFP minus EV equal to what actually? KT into ln of NV by NA. What is the value of KT at room temperature? 0.026 ln of NV. NV is nothing but 26.6 into 10 power 18 by NA. NA is nothing but 10 power 14. This is 10 power 18 actually. So the answer is 0.324 electron volt. Actually, again here I am writing this one actually. 0.026 ln of 26.6 into 10 power 18 by 10 power 14, right. Now copy. Right. Next question, question number 5. Question number 5. Yeah, write in the question. An n-type semiconductor has following data. An n-type semiconductor has following data. Hole and electron mobility ratio is 0.4. 0.4. Doping concentration is 4.2 into 10 power 8 per centimeter cube. Next. Intrinsic concentration is 1.5 into 10 power 4 per centimeter cube. 1.5 into 10 power 4 per centimeter cube. Find ratio of conductivity of doped sample with respect to undoped sample is right. See here, all of you read the question. Actually, the n-type semiconductor has the following data. They given hole and electron mobility ratio. That means mu p by mu n. How much? 0.4. Also, they given a doping concentration, that is Nd equal to 4.2 into 10 power 8. Also, they given Ni equal to 1.5 into 10 power 4 per centimeter cube. Yeah, what we want to calculate actually, ratio of the doped sample, conductivity of doped sample, ratio of conductivity of doped sample with respect to undoped sample. See here, what is our doped sample? N-type sample. That means sigma n to the undoped. Undoped sample is nothing but intrinsic, right? Nothing but sigma n. This is we want to calculate sigma n by sigma n. See, actually, what is the sigma n value actually? Sigma n is nothing but Nd into E into mu n. What is sigma I? Sigma I is nothing but Ni into E into mu n plus mu p. Here E cancel and Nd by Ni into, here common the mu n value here, that is 1 by 1 plus mu p by mu n. What is the ND value here actually? So ND is nothing but how much? They given 4.2 into 10 to the power of 10 power 8. Ni is nothing but 1.5 into 10 power 4 into 1 by 1 plus mu p by mu n, that is 0.4. So which is equal to 2 into 10 to the power of 4. This is the conductivity of doped sample with respect to undoped sample. Copy? Yeah. Next topic. Compensated semiconductor. Compensated semiconductor. Yeah, so no. See, compensated semiconductor is nothing but, see, when the semiconductor is doped with both trivalent as well as pentavalent. When the semiconductor is doped with both trivalent and pentavalent actually, then, okay, such a semiconductor is called as what actually? Compensated semiconductor. See, up to so far what we discussed actually, the semiconductor is doped with either trivalent or pentavalent. Now, my semiconductor is subjected or doped with both trivalent or pentavalent, then this semiconductor acts as a N-type or P-type or intrinsic semiconductor, depending upon what actually? Relative concentration. Depending upon relative concentration. Okay, you know, such a semiconductor is called as what actually? Compensated semiconductor. And also this compensated semiconductor also can satisfy the charge neutrality or electrical neutrality. Actually, what is the charge neutrality or electrical neutrality? Net amount of negative charge equal to net amount of positive charge. See, if it is an intrinsic semiconductor, actually, what is the charge neutrality equation? Actually, N equal to P, right? Now here, my semiconductor is doped with what actually? Both trivalent, pentavalent, right? Now I can add the donor impurities as well as acceptor impurities, right? Now what is this? This is the charge neutrality equation of a compensated semiconductor, right? I think if you go for semiconductors doped with only trivalent, then what is the charge neutrality equation actually? Na plus N equal to P. If semiconductor is subjected to only pentavalent, then this is the charge neutrality equation, right? Now what is this? This is the semiconductor, okay, doped with both trivalent as well as pentavalent. That is Na plus N equal to P plus N, right? This is equation 1. Write on the notes. Write in your notes. When the semiconductor is doped with, both trivalent and pentavalent. Both trivalent and pentavalent. Both trivalent and pentavalent. Such a semiconductor is called as compensated semiconductor. Compensated semiconductor. in bracket N-type or P-type or intrinsic. N-type or P-type or intrinsic. Yeah, bracket close. Next point, such a semiconductor also satisfies, continue, such a semiconductor also satisfies charge neutrality or electrical neutrality. Charge neutrality or electrical neutrality. Charge neutrality or electrical neutrality. Right? Yeah. Copy this one. Right. See here. For example, if the semiconductor is doped with equal acceptors, equal number of acceptors as well as equal number of donors. Right? If the semiconductor is doped with equal number of acceptors as well as equal number of donors, then what is the condition actually? Then N equal to P. Right? If N equal to P means what is our compensated semiconductor? The compensated semiconductor acts as a intrinsic semiconductor. Intrinsic semiconductor. Right? This is the case 1. Now case 2. See here, if acceptor concentration is greater than donor concentration. If acceptor concentration is greater than donor concentration, means we are doping with both acceptor and donor. But what will be the condition actually? Na is greater than Nd. Then what is the semiconductor actually? The semiconductor acts as a P-type semiconductor. The semiconductor acts as a P-type semiconductor. Right? And what will be the net impurity concentration actually? Net impurity concentration. Net impurity concentration is Na minus Nd. Right? And how to calculate the hole concentration and electron concentration in this compensated P-type semiconductor? Right? Already we derived. Tell me, if the semiconductor is doped with only acceptor, then what is the hole concentration equation actually? Na plus under root Na square plus 4 Ni square by 2. Already we derived this equation, right? This is what actually, if the semiconductor is doped with only trivalent, but what is my semiconductor? Compensated semiconductor, right? That means my semiconductor is doped with both acceptor as well as donor. But what is the condition? Na is greater than Nd. Then how to calculate the whole concentration? Same, just this replaced with Na is replaced with what actually? Na minus Nd. This one also replaced with Na minus Nd whole square. Right. And what about electron concentration actually? Np equal to what actually? Np is nothing but Ni square by Pp. Right. These two are called as what actually? Exact formulas. Right. Next, I can also go for approximation actually. What is an approximation? If Na minus Nd is far greater than Ni, then what about whole concentration? Actually, the whole concentration is approximately equal to Na minus Nd. And what should be the electron concentration actually? Electron concentration is nothing but Np equal to Ni square by Na minus Nd. These two are called as approximate formulas. This is for what actually? Compensated P-type semiconductor, right? Now the third case also be there actually. Third case. What is the third case actually? The third case is, right, if Nd is greater than Na. See, if Nd is greater than Na, then what is the semiconductor actually? The semiconductor acts as a N-type semiconductor, right? And what will be the net impurity concentration actually? Net impurity concentration. Net impurity concentration in case of compensated N-type, that is Nd minus Na. Right. In case of compensated N-type, what are the formulas for majority and minority concentration actually? That is Nn equal to Nd minus Na plus under root Nd minus Na whole square plus 4 Ni square by 2. Right. Now, what about the whole concentration? Actually, Pn equal to Ni square by Na. Actually, these two are called as what? Exact formula. These two are called as exact formula. Next, I can also go for approximation. Actually, what is an approximation actually? See, to get the approximation here, I am considering one condition, that is Nd minus Na is far greater than Ni. Right? Then, what about the Pn actually here? What about the Nn? Actually, Nn equal to approximately equal to Nd minus Na. And what about the Pn? Actually, the Pn is nothing but Ni square by Nd minus Na. These two formulas are called as approximation formulas. Copy? Copy case 1, case 2, case 3. Right. Next, write in a question in workbook. Question number 6. Write in a question. A germanium sample is doped with 10 power 14 phosphorus atoms, 10 power 14 phosphorus atoms and 7 into 10 power 13 boron atoms, 7 into 10 power 13 boron atoms, right. If Ni equal to 2.5 into 10 power 13 per centimeter cube, 2.5 into 10 power 13 per centimeter cube, comma, mu n equal to 4,000 centimeter square per v second, comma, mu p equal to 2000 centimeter square per v second, calculate first bit, carrier concentration, second bit, conductivity, right. See, I'll have to read the question once actually. They given a pure germanium sample, right? Given a pure germanium sample. It is doped with what actually? It is doped with 10 power 14 phosphorus, right? Also, it is doped with what actually? 7 into 10 power 13 boron, right? So phosphorus means I think this is the donor concentration. Boron means this is the acceptor concentration, right? Donor concentration is 10 power 14, 10 power 14 and acceptor concentration is 7 into 10 power 13. Also, they given a Ni. Ni equal to how much actually? Ni is nothing but 2.5 into 10 power 13 per centimeter cube. Also, they given a mu n. Mu n is nothing but 4000 centimeter square per volt second, and the mu p equal to 2000 centimeter square per volt second, right? Uh, what we want to calculate actually carrier concentration and conductivity. See, for calculation of carrier concentration, we have two formulas, exact formula and approximate formula, right? Here, which formula is suitable? So here, before calculation of carrier concentration, actually see this. Here the semiconductor is doped with both pentavalent as well as trivalent. That means what it is? It is a compensated semiconductor. Compensated semiconductor it is. Right? Here, in compensated semiconductor, actually, what is the condition? Nd is 10 power 14, Na is 10 power 13. That means clearly, what it is actually? Nd is greater than Na. Nd is greater than Na means what is a semiconductor? Actually, the semiconductor acts as a N-type semiconductor, right? And what should be the net impurity concentration? Actually, net impurity concentration. Net impurity concentration is Nd minus Na, right? What is Nd here actually? Nd is nothing but 10 power 14, Na is nothing but 7 into 10 power 13. And what is this value actually? 3 into 10 power 13 per centimeter cube. 3 into 10 power 13 per centimeter cube, right? This is the net impurity concentration. Now here, how to calculate the carrier concentration? See, already I told now for calculation of carrier concentration, we have two formulas, exact and approx. Here, for this application actually, exact or approximate. How to know? See this, Ni is 10 power 13, 2.5 into 10 power 13, and net impurity concentration is 3 into 10 power 13. That means here we can go for exact formula, right? What is an exact formula actually? Exact formula is nothing but Nn equal to Nd minus Na plus under root Nd minus Na whole square plus 4Ni square by 2. What is Nd minus Na actually? Nd minus Na is nothing but 3 into 10 power 13 plus under root Nd minus Na, that is 3 into 10 power 13 whole square plus 4 into Ni, that is 2.5 into 10 power 13 whole square by 2. So which is equal to 4.4 into 10 power 13 per centimeter cube. And how to calculate the whole concentration? Actually, the Pn equal to Ni square by Nn. Ni is nothing but 2.5 into 10 power 13 whole square by Ni, that is 4.4 into 10 power 13. So which is equal to 1.4 into 10 to the power of 13 per centimeter cube. This is the carrier concentration. Carrier concentration means both free electron concentration as well as hole concentration. This is the first bit. And what is the second bit actually? Conductivity. Yeah. What is the equation of conductivity? Actually, sigma n equal to Nn into E into mu n plus Pn into E into mu p. What is Nn actually? 4.4 into 10 to the power of 13 charge of electron, 1.6 into 10 power minus 19, mu n 4000, Pn is nothing but 1.4 into 10 power 13 charge of electron, 1.6 into 10 to the power of minus 19, mu p 2000, right, which is equal to 0.032 ohm centimeter whole power inverse. This is the conductivity of that compensated semiconductor, right? Copy. Yeah. Next topic. Calculation of heading. Calculation of Fermi level of doped sample with respect to undoped sample. The sample is nothing but semiconductor, or calculation of extrinsic Fermi level with respect to intrinsic Fermi level. Calculation of extrinsic Fermi level with respect to intrinsic Fermi level, right? See here, calculation of Fermi level of doped sample with respect to undoped sample. Actually, what is the doped sample? Doped sample is nothing but, it may be n-type or p-type. What is undoped sample? Undoped sample is nothing but intrinsic sample, right? Here Fermi level of doped sample is nothing but that may be EFN or EFP. Okay. With respect to undoped sample is nothing but EFI. Actually, what we want to calculate means EFN minus EFI or EFP minus EFI. This is we want to calculate, right? See, for calculation of this one, so first I can define for any semiconductor. See, so for any semiconductor, what is the electron concentration equation actually? N equal NC into E power minus of EC minus EF by KT, right? This is equation 1. And what about the whole concentration? Actually, the whole concentration NV equal to E power EF minus EV by KT. This is equation 2. Right? Okay. Now, first here we want to calculate extrinsic Fermi level with respect to intrinsic, right? Here I am considering N-type semiconductor, or you may consider P-type semiconductor also, right? For N-type semiconductor. See, tell me for N-type semiconductor, what is the electron concentration equation? N equal to approximately what? Na. And what about the EF actually? EF equal to what? EFN. EFN, right? Now substitute this is equation 3. Now from equation 1 and equation 3. Now Na is approximately equal to Nc into E power. What about Ec minus EF become what actually? EFN by kT. This is equation 4, right? Now similarly can define the intrinsic semiconductor. Actually see for intrinsic semiconductor, what about the electron concentration? Actually electron concentration is equal to what? Ni. And what about the EF actually here? EF equal to what? EFI. So N equal to Ni and EF equal to EFI, right? Now see all of you here, N equal to Ni means this is Ni is approximately equal to, just wait. Now you can consider this one as equation 5, right? Now from equation 1 and 5, right? Now Ni is approximately equal to Nc into E power Ec minus this EF become what actually? EFI by kT. Now this is equation 6, right? Now here what we want to calculate? Extrinsic Fermi level with respect to intrinsic. For calculation of this one actually, so consider like this. Consider equation 4 by equation 6, right? Now this is Nd by Ni is equal to Nc into E power minus of Ec minus EFN by kT. This is Nc into E power Ec minus EFI by kT. NC cancel. Now Nd by Ne is equal to E power minus Cc cancel, minus of minus plus, this is EFN, minus of minus plus, it become minus EFI by kT, right? Now take logarithmic on both sides. Now EFN minus EFI is equal to by kT ln of Nd by Ni, right? Now what is the final expression actually here? The final expression, that is EFN minus EFI is equal to kT into ln of Nd by Ni. So this is what actually, so this is the calculation of Fermi level, okay, Fermi level of doped sample with respect to undoped sample, or we can also say extrinsic Fermi level with respect to intrinsic Fermi level. This is with respect to N type actually. Similarly for P type. Similarly for P type semiconductor. See for P type semiconductor, see all of you. For P type semiconductor actually, what about this EFN become actually EFP minus EFI kT into ln of this Nd become what actually? Na by Na, but we get minus also here, because in case of P type the expression is E power minus of EF, right? So we will get the minus. So this is what actually for P type. This is the extrinsic Fermi level, nothing but P type with respect to intrinsic Fermi level. Right? Copy. Very important derivation. Write in a question in workbook, classroom workbook, question number 7. A pure silicon sample is doped with, a pure silicon sample is doped with 10 power 17 arsenic atoms, 10 power 17 arsenic atoms per centimeter cube. Find Fermi level of doped sample, Fermi level of doped sample with respect to undoped sample, undoped sample. If Ni equal to 1.5 into 10 power 10, 1.5 into 10 power 10 per centimeter cube, right? Yeah. First of all, what is the given question actually here? They given a pure silicon sample, right? Yeah. They given a pure silicon sample. It is doped with what actually? Arsenic. Huh. It is doped with arsenic means it become n-type semiconductor because it is a pentavalent. Now the semiconductor is n-type. How much amount actually? 10 power 17. That means Nd they given 10 power 17 per centimeter cube. Okay. Find Fermi level of doped sample with respect to undoped sample if Ni equal to 1.5 into 10 power 10 per centimeter cube. Right. Actually, what we want to calculate actually Fermi level of doped sample. What is the doped sample? N-type. Fermi level of N-type means EFN. With respect to undoped, undoped is nothing but EFI. What is the value of EFN minus EFI actually? KT into ln of Nd by Ni. What is the KT value at room temperature actually? 0.026. Here actually did not mention room temperature or not actually, but we should consider generally in room temperature only if it will not mention, right? So KT value at room temperature is 0.026 ln of Nd. Nd is nothing but 10 power 17. Ni is 1.5 into 10 power 10. Now what is this value? 0.408 electron volt. This is what actually extrinsic Fermi level with respect to intrinsic. Nothing but doped sample with respect to undoped sample. Copy? Right. Yes. Thank you. To be continued in next lecture actually.